Hi everyone and welcome back. In this video we're going to look at higher derivatives, concavity, and the second derivative test. I would like you to recall that derivatives were used to determine intervals where the function is increasing or decreasing. We also used it to determine maxes and mins. It's important for us to know how the rate of increase or decrease is also changing, and we can accomplish this by determining the rate of change of the derivative of the function. So in other words, we can find the derivative of the derivative, which is called the second derivative. So suppose a friend is trying to get you to invest in the stock of a young company. The following function represents the price, P of t, of the company's stock since it became available 2 years ago. P of t equals 17 plus t to the 1/2, where t is the number of months since the stock became available. He claims that the price of the stock is always increasing and that you will make a fortune on it. Verify his claims. Is the price of the stock increasing? How fast and how much will you make if you invest now? So since I'm looking at increasing, decreasing, I want to find the derivative. So I'm going to find the derivative of P of t, and we know that that would just be 1/2 t to the negative 1/2 power. Okay, which I can write as 1 over 2 times the square root of t. Now, this is always going to be positive because the square root of t has to be greater than 0 when t is greater than 0. Okay, so therefore, P of t is always going to be increasing if it's always going to be positive. But how fast is it increasing? Okay, because your friend claims the stock is always increasing and you'll make a fortune on it. So I would want to know how fast. You can have a function increase, but it can increase at a very small amount. So in the case of money, you wouldn't make that much money, as this person claims. All right, so if I was to take that function and now find the second derivative. Okay, so I'm just going to take the derivative of my derivative. If I apply the power rule, I would get negative 1/4 t to the negative 3/2, which we know we can write as negative 1 over 4 times the square root of t cubed. Okay, so now I can see here I have this negative introduced. So the second derivative is negative when t is greater than 0, right? So what does that tell me? It tells me that the rate of increase in the price does decrease for t is greater than 0. Okay, so therefore, if the price of the company's stock, it's not going to drop, but the amount of return will not be the fortune that your friend predicts. Okay, so I can show you some examples of why that is. So let's say we wanted to check how much the price would increase, maybe, I don't know, 2 years from now, right? Because that's what he claims in the problem. So 2 years would be 24 months. So I'm just going to find where t is equal to 24 into my original function, right? So p of 24 would just be, let's see, 17 plus 24 to the 1/2 power. And if we need a calculator for that. So 17 plus 24 and then to the 1/2 power. Remember to put the 1/2 in parentheses. We get 21.898, so it's about $21.90. Okay. How about a year after that? So a year after that would be another 12 months. So that would be 36 months. This time I'm going to find P of 36. So now it's going to be 17 plus 36 to the 1/2 power, which is only $23. So as you can see, the stock still increased, like we said, okay, but it only increased by what, $1.10 in 1 year. So what does that mean? It means like if you bought 100 shares, okay, if you could afford that, your investment now after 2 years would be or now at this time would be $2,300, right, in a year. So that's what your investment would be worth. Okay, that's in 1 year from now. We're pretending that 2 years already elapsed. So that's only an increase of about $110, right? So the only investors to make a lot of money would be anybody that bought earlier when the rate of increase was much greater. So that gives us a little preview of what we're going to be looking at here. We're going to be looking at higher order derivatives and how they help us determine rate of change, right? Rate of change is slope. Derivatives give us slopes. So when I say higher derivatives, let's say we start off with a function f of x equals x to the 4th plus 2x to the 3rd plus 3x squared minus 5x plus 7. We know that we can find the derivative using just the power rule. So we would get 4x to the 3rd plus 6x squared plus 6x minus 5. Well, I can take the derivative of that. So I'm going to take the derivative again. That would give me the second derivative. So I would have 12x squared plus 12x plus 6. And I can go again. I can find the derivative of the second derivative. So this would be the third derivative. You'd have 24x plus 12. And I can even go one more time. So anytime we get beyond 3, if you want to show the fourth derivative or higher, you put a little 4 in parentheses there. Okay, and that should be x. And that would just be 24. And then I can't go any further, right? Because the derivative of 24 is 0. So this right here is called the first derivative. This would be the second, the third, and the fourth. So some notation, the second derivative of a function f of x can be written in the following ways. So using the notation I showed you, so we would have f double prime of x. You could also write it as d squared y over dx squared. So the second derivative of y with respect to x. You could also use this notation, okay, which we've seen show up in the book occasionally. So the only difference is there's a 2, and that 2 means second derivative of x, or of f of x with respect to x, okay, etc. So if I wanted to find the third derivative, we would change these to 3s. Anytime you have the exponent or the derivative is 4 or higher, so we'll just call the derivative n, the nth derivative. For n is greater than or equal to 4, the nth derivative is written f to the n and then of x. So that's the nth derivative of f. And that's only for derivatives 4 or higher. All right, let's practice a little bit. So here we've got f of x equals x cubed plus 6x squared minus 9x plus 8, right? Polynomial, we want to find the second derivative, so f double prime of x. And to do that, I'm going to first find f prime and then go from there. So the first derivative would just give me 3x squared plus 12x minus 9. And then I'm going to take the derivative of that, which would give me 6x plus 12. Okay, and I want to find f double prime of 0, so all I have to do is plug 0 into my second derivative, and we get 12. Okay, what I'd like you to do now is pause the video and practice the check your understanding. You're finding f double prime of 1, and then you can unpause the video when you're ready to move on. In this next set of examples, we want to find the second derivative for the functions defined as follows. For letter A, I've got f of x equals the quantity x squared minus 1 squared. So I have a quantity squared, so which rule would I have to use? You guessed it, the chain rule. Or you could use the general power rule, right, which consists of the power rule and the chain rule. So I'm just going to use the general power rule because it's much easier. For our first derivative, it would just be 2, right? The power comes down. It would be 2 times x squared minus 1, and then decrease the exponent and multiply it by the derivative of the inside, which would just be 2x. So I can combine that and make it 4x times the quantity x squared minus 1. Okay? Now I need to find the second derivative, but you can see here the first consists of a product. So you guessed it, I have to use the product rule. So I'm going to have u is equal to 4x, and v is going to be x squared minus 1. So my derivative of 4x is just 4, and the derivative of x squared minus 1 is 2x. So now to find my second derivative, I'm going to have u times v prime, and then plus v times u prime. So here we would get x squared, and then plus 4x squared minus 4, which I can combine and just make that 12x squared minus 4. Now in letter B, I've got g of x equals 4x times the natural log of x. So again, I have a product. Before I can even find the first derivative, I need to use the product rule. So we're going to let u equal 4x, and then v is going to be ln x. So u prime is just 4, and the derivative of ln x, if you'll remember, is 1 over x. So to find my derivative, I'm going to have 4x times 1 over x plus the natural log of x times 4. So that would just give me 4 plus 4 times the natural log of x. Okay, and I'm not done because I need to find the second derivative. So I know that the derivative of 4 is just 0, right? So I don't have to worry about that. I know that the derivative of this piece is just going to be 4 times 1 over x. So that just gives me 4 over x. Okay, you can unpause the video and you can, or pause the video rather, and try check your understanding number 2. And then you can unpause when you're ready to move on. We're going to talk about velocity and acceleration. I'd like you to recall that the first derivative of a function, remember, represents the rate of change of the function. Okay, rate of change is just slope, right? Derivatives and slopes are related. The second derivative then represents the rate of change of the first derivative. So if a function describes the position of, let's say, a vehicle, and we'll pretend it's just along a straight line at time t, then the first derivative is going to give the velocity of the vehicle. So in other words, if y equals s of t describes the position of the vehicle at time t, then v of t is going to equal s prime of t, which gives the velocity at time t. So the derivative of speed is going to give us velocity. Recall also the velocity is the rate of change of distance with respect to time. And the difference between velocity and speed is velocity can be positive or negative. Speed can only be positive. So a negative velocity means that you're traveling in a negative direction, which if you're in a car, that would just mean you're backing up, right? Positive velocity indicates that you're traveling forward from the starting point. The instantaneous rate of change of velocity is acceleration. So if I take the derivative of my velocity function, I get acceleration. Since instantaneous rate of change is the same as the derivative, acceleration is the derivative of velocity. So if a of t represents the acceleration at time t, then a of t is just the derivative of the velocity with respect to time. So that's just the second derivative of speed, right? If you take the first derivative of speed, it gives us velocity. So s prime of t equals v of t, right? If I take the derivative of velocity, it's going to give me acceleration, right? Well, if I take the derivative of this, it's just the second derivative of that. So the second derivative of speed would just give me acceleration. Okay, a positive velocity and a positive acceleration means the velocity is increasing. So the vehicle would be speeding up. If you have positive velocity and negative acceleration, it just means the vehicle is slowing down. Negative velocity and a positive acceleration means the vehicle is backing up while it's slowing down. And a negative velocity and a negative acceleration means the vehicle is backing up and speeding up. Suppose a car is moving in a straight line with its position from a starting point at time t in seconds given by s of t equals t cubed minus 2t squared minus 7t plus 9. If I want to find the velocity at any time t, right, I just need to take the derivative of speed. So velocity is equal to s prime, and s is t cubed minus 2t squared minus 7t plus 9. So the derivative of that is just going to be 3t squared minus 4t minus 7. If I want to find the acceleration at any time t, that's going to be the derivative of velocity, which would just be the second derivative of speed. So that's just going to be 6t minus 4. Now I want to find the time intervals for t is greater than or equal to 0 when the car is going forward or backward. Okay. So we have to remember that the car is moving in a straight line. So positive velocity would tell me that the car is moving forward. And a negative velocity would tell me that the car is moving backwards. So I want to find the intervals where the velocity is positive and negative, and we learned how to do that, right, in the first section. So I'm going to take my velocity, which is just 3t squared minus 4t minus 7, and I'm going to set that equal to 0 and find my critical values. This actually will factor into 3t minus 7 times t plus 1. Okay, now when I set these equal to 0, I get t equals 7/3 and t equals -1. I'm going to ignore the time equals -1 because we're looking for where t is greater than or equal to 0. So this is more like an extraneous solution. So the only critical value we're going to look at is going to be 7/3. Okay, so I'm going to pick a number to the left of it to test, like 0, and then maybe 3. And we're going to look at the signs, right? So when I plug a 0 in here, I'm going to get a negative times a positive, which is a negative. So the function is decreasing on that interval from -infinity to 7/3. Actually, from 0 to 7/3, right? Because time can't be less than 0. So the function will decrease from 0 to 7/3. And then the function will increase because if I plug in a 3 into t here, you get a positive. So that means it's going to increase from 7/3 all the way to whenever the car stops, right? So we'll just say to infinity. So what this tells me is, since it's negative, the car is going to be backing up for the first 7/3 seconds. So that's like 2 1/3 seconds, 2.3 seconds. Then it's going to go forward. Now we want to find the time intervals, again, for t is greater than or equal to 0 when the car is speeding up or slowing down. Okay, so speeding up, slowing down, we're talking about acceleration, right? So the car speeds up when the velocity and the acceleration have the same signs. So that means cars speeding up. Okay. It's going to slow down when you have opposite signs. So I need to find the acceleration, which we found in part B. It's just 6t minus 4. And again, I'm going to set that equal to 0. Let me shrink this so we have some room. If I solve this, let's see, I would add 4 to both sides. I get 4/6 or 2/3. Okay, so I'm going to use 2/3, and then I'm also going to use 7/3 from my last, the last part, right? I need to incorporate that as well. Okay, and we'll pick some test points. 0 is the lowest we can pick, and then maybe pick like a 1, and then we'll do 3 again, okay? This time we're plugging it into the second derivative. So if I plug a 0 in, I get a -4. So that's going to be negative. Okay, so let me do this. Let me slide this up, and I'll label these to make it a little easier for you all. So why don't we put the sign of acceleration here, and then we'll look at the sign of velocity here, because we need to look at both signs to determine whether the car is going to be speeding up or slowing down, right? So if I plug a negative in, if I plug 0 in here, I get a negative. If I plug a 1 in, I get a positive. 6 times 1 is 6, minus 4 is positive 2. If I plug in a 3, I also get a positive. Okay, and then I already know, part of this anyway, for v of t, what I would have gotten. So I know that when you plugged in a 3, right, v of t was positive. And when I plugged in 0, I know v of t was negative. When I plug in a 1, if I go back to v of t and plug in 1, I get a negative times a positive, which is a negative. Okay, so what I can see here is that the signs are the same here and the signs are the same here, and they're different right here. Okay, so when the signs are the same, it means that the car is speeding up. When the signs are different, it's slowing down. So if I was to interpret this, it would tell me that the car is speeding up for the first 2/3 seconds, right? And after 7/3 seconds, so after 2.3 seconds, it's going to start to speed up. So it speeds up and then it slows down between 2/3 and 7/3, and then it speeds up again. Okay, so what does that mean? It means that the car is accelerating as it's backing up. That's for the first 2/3 seconds. Then it's going to slow down to a stop, right? And then at 7/3 seconds, it's going to be put into drive, so forward, and it's going to speed up again. Okay, you can pause the video and try the next problem on your own, and then unpause, and we're going to talk about an important concept called concavity. So if you'll remember, all this talk about derivatives, right? The first derivative has been used to show where a function's increasing or decreasing, and we also learned that we can use it to determine where there's extrema, if any, right? And extrema, again, are maxes and mins. The second derivative, we learned, gives us the rate of change of the first derivative. So it basically tells us how fast the function's increasing or decreasing. The rate of change of the second derivative affects the shape of the graph. So intuitively, we say that the graph is concave upward on an interval if it opens up, and concave downward if it opens down. So you can see here, the graph is opening downward, so that's concave downward. Here, the graph's opening up, so concave upward. And you can see the same thing in that picture there. So we say a function is concave upward on an interval, and we'll call the interval AB again, just to be consistent throughout the section. If the graph of the function lies above its tangent line at each point AB. Okay, so you can see here, right? I'm going to take this graph here, and this is concave downward, right? And I can see that because the graph of the function lies, sorry, we're looking at upwards. So right here, it's upward, right? And we can see that the graph of the function lies above the tangent line. Okay, now going back to this, you can figure out what I'm going to write for downward, that the graph of the function is going to lie below the tangent line at each of the points AB. Okay, so this is going to be the same thing on an interval AB. If the graph of the function lies below its tangent at each point AB. Now you can see in this graph, it's concave downward and concave upward in that interval from A to B. So at some point, the graph switches concavity, and the place where it switches concavity or changes concavity is called the inflection point. So you can also see here the connection between increasing and decreasing and concavity. So we can see that the function's increasing and then it's decreasing. So where the function changes signs, increasing is plus, decreasing is minus, there's going to be an inflection point. And it goes from decreasing to increasing. So there's an inflection point, okay, whenever the signs change for the derivative. Okay, so here's some other visuals for us, right? We have negative slope, zero slope for a horizontal line, positive slope, and the slope is given by the derivative. In both of these graphs, we have concave upward, right? Notice that the slopes are increasing in both cases, right? They're increasing in the cases. That means that the derivative has to be positive, okay? It's going to be concave up if the second derivative is positive. And here we can see that we've got, again, positive and negative slopes, zero slopes, decreasing negative slopes. So the function, again, is decreasing, right, if the derivative is negative. And we'll have a function that's concave downward if its second derivative is negative. So concave up, second derivative is positive. Concave down, second derivative is negative. So we have these tests that we use for concavity. Suppose that a function f has a first and second derivative each. Actually, I'll say first and second derivative at each point in an open interval. If the second derivative of f is positive for each x in the interval, then that tells me that f is concave upward. And you can probably guess that if the second derivative is less than 0 for each x in the interval, f is going to be concave downward. Okay, so the second derivative here is going to be negative, concave downward. Second derivative of this function is negative, concave downward. Here, if we were to take the second derivative of this function, it would be positive, so it's concave upward. Second derivative again, positive, concave upward. So here's a function. We want to find all the intervals where that function is concave upward or downward, and also find all the inflection points. Okay, so I need to find the second derivative. That's going to tell me all of this. So before you find the second derivative, you got to find the first, and we're just using the power rule. So we get 4x cubed minus 24x squared plus 36x. Okay, and then I want to take the derivative of that. So that would be 12x squared minus 48x plus 36. Okay, let's find our critical values. So we're going to set this equal to 0. Let's see, I can factor 12 out of there, and I'm left with x squared minus 4x plus 3. And this is really easy to factor. It's just going to be x minus 1 times x minus 3. So we get x equals 1 and 3 for our critical points. All right, let's pick our test points. So 0, 2, and 4. I'm going to plug those values into my second derivative, and it's going to tell me about the original function if it's concave upward or downward. So if I plug in a 0 into my second derivative, right, I would get a 0 minus 1, that's -1. A 0 minus 3 is -3. A negative times a negative times a positive gives me a positive. So that tells me from -infinity to 0 that or from -infinity to 1, it's going to be concave up. Okay? If I plug in a 2 into my second derivative, I get a positive times a negative times a positive. So that's a negative. This is going to be concave down from 1 to 3. And then if I plug in 4, you would get all positives. So this is going to be concave up. Okay, so I know that the function is concave up from -infinity to 1 and from 3 to infinity. And then I know that it's going to be concave downward from 1 to 3. Okay, now let's talk about inflection points. So what I need to do to find the inflection point is I just need to look to see where f double prime changes signs. Okay, where is it changing signs? Well, it's changing signs right here at 1 because it goes from positive to negative, and then also at 3 from negative to positive. So all I need to do is find f of 1 and f of 3. Okay, so if I plug in a 1 into my original function, you get 1 to the 4th minus 8 times 1 cubed plus 18 times 1 squared. And that's going to give us 11. Okay, and then if I plug in a 3, I would get 3 to the 4th minus 8 times 3 cubed plus 18 times 3 squared. And that's going to give us 37. So I've got two inflection points. One of them is going to be at 111, and the other is going to be at 337. Okay, let's take a look here at the graph and see what we get. So if I was to use this function here, x to the 4th, and then it's minus 8x cubed plus 18x squared. You can see here that it's concave up from -infinity to 1. And then it's concave downward from 1 to 3. If I can, it's not letting me zoom out. Okay, so again, it's concave upward from -infinity to 1. And then it's also concave upward from 3 to infinity. And then it's going to be concave downward from 1 to 3. And it's kind of hard to see on here. But you can see here how there's like all these, like right there is like 3, right? It's kind of hard to get to that point. And then over here is as it gets closer and closer to 1, -1 rather. So the graph is not very helpful. That's not a good graph to look at, but you get the idea. All right, if you could, you can pause the video and look at the check your understanding number 4, and then unpause when you're ready to look at example number 6. So here we're trying to find open intervals where the following functions are concave upward or concave downward, and then find any inflection points. Okay, so you can see here, I need to find the second derivative. To do that, I'm going to have to use the general power rule. And then I would do that again. And I get 12 times x minus 1 squared. Okay, I need to find my critical value, so I'm just going to set x minus 1 squared equal to 0. And of course, you just get x equals 1. Okay, so 1's my critical value. And I'm going to plug in some test points, so maybe like 2 and 0. If I plug a 0 in here and square it, I get a positive. And if I plug a 2 in and square it, I get a positive. So this tells me that the graph is always going to be concave upward. Okay, the graph doesn't change concavity, so that also means there's no inflection points. In my next function, okay, I'm just going to use the power rule. That's just going to be 1/3 x to the negative 2/3. And then my second derivative, if I do negative 2/3 times 1/3, I get negative 2/9 x to the, let's see, negative 5/3, which I can just write as negative 2 over 9 x to the positive 5/3 power. Okay, so we saw problems like this before where this can never equal 0 because of the simple fact that it's negative 2 divided by something. But you notice in the denominator, x could be 0, right? So if I set 9x to the 5/3 equal to 0, you end up with x equals 0 if you solve that for x. Okay, so I'm going to use 0 as my critical point, and I'm going to pick a number before it and a number after it. If I plug in negative 1, the cubed root of negative 1 is negative 1. To the 5th is still negative 1. Negative 1 times 9 is negative 9. You have a negative divided by a negative, which is a positive. And then if I plug in a 1, you end up with a negative divided by a positive, which is a negative. So I can see here that the sign does change from positive to negative. So that tells me that it's going to be concave up from negative infinity to 0. It's going to be concave down from 0 to infinity. And it also tells me that there's an inflection point since the sign's changing. Okay, I'm going to plug my critical value into my original function. 0 to the 1/3 power is just 0. So there's going to be an inflection point at 0, 0. All right, so last concept in this section, second derivative test. Concavity can be used to help us decide whether a given critical value produces a relative max or min. So we're going to let f double prime of x exist on some open interval containing C, and we're going to let f prime of C equals 0. So the second derivative test tells us that if f double prime of c is less than 0, f of c is going to be a relative max. If f double prime of c is greater than 0, then f of c is going to be a relative min. And if f double prime of c equals 0, or f double prime of c does not exist, then that means this test doesn't give us any information about extrema. So that tells us then we need to use the first derivative test. Okay, so in this last example, and thank you for hanging in there to this point, find all relative extrema and inflection points for the following function. Okay, so we've got this function 4x to the third plus 7x squared minus 10x plus 8. So the first thing I want to do is find where that derivative equals 0, right? Step 1. So how do I find f prime? It's just going to be 12x squared plus 14x minus 10. Okay, and I'm going to set that equal to 0. I can factor a 2 out of there. And then I can also factor this. I would get 3x plus 5 times 2x minus 1. And I know if I set those equal to 0, I would get x equals negative 5/3 and x equals positive 1/2. Okay, now I'm going to apply the second derivative test. So the derivative of this is going to be 24x plus 14. Okay, so what I'm going to do now is I'm going to plug negative 5/3 into the second derivative. Okay, and let's see, this would give us 3 into 24 is 8 times negative 5 is negative 40 plus 14. That's going to give me negative 26, which is less than 0, okay? So that tells me there's going to be a relative max. And the way I find it, remember, is I'm going to plug negative 5/3 into my original function. And you end up with 25.59. So that tells me there's a relative maximum at negative 5/3, comma 25.59. Now I want to do the same thing for 1/2. Okay, if I plug 1/2 into my second derivative, I end up with 26, which is greater than 0. So that tells me there's going to be a relative min. To find the relative min, I'm going to plug 1/2 back into my function, my original function. And when I do that, I get 5.25. So there's a relative min at 1/2, comma 5.25. Okay, so we found maxes and mins, which are extrema. Now I want to look for inflection points. Okay, so again, we're going to go to the second derivative for that. Set it equal to 0. Let's see, subtract 10. You would get negative, sorry, that should be 14. So subtract 14, that would be negative 14 over 24, or negative 7 over 12. Okay, so I want to look for sign changes, right? I would plug my test points in. So maybe like -1 and 0. Okay, and I'm plugging them into my second derivative. So a negative plus -24 plus 14 leaves me with a negative still. So that tells me it's going to be concave down, the function, right? And if I plug in 0, I get a positive. That tells me it's going to be concave up. Okay, so since it's changing signs, that tells me that is an inflection point. And to find the inflection point, I'm just going to plug -7/12 into the original function. And when I do that, you can use your table for this. You get 15.42. So that means there's an inflection point at -7/12, comma 15.42. Okay, and there's a problem for you all to practice here, so I strongly encourage you to do that. The last section in this unit is curve sketching, so we'll look at that in the next video, and we're going to take all of the information we learned in the past 3 units and apply it to sketching these curves in 5.4. Okay, enjoy your day, everyone.